Have you ever wondered how neural networks actually learn? How does a machine go from making random guesses to recognizing faces, translating languages, or even beating world champions at chess? The secret lies in a powerful algorithm called backpropagation, the backbone of modern deep learning. Today, we're going to demystify this fundamental concept and understand exactly how neural networks learn from their mistakes. In this video, we'll cover what backpropagation is, why it's so important, walk through the mathematical intuition, see how it works step by step, and understand why it's the driving force behind today's AI revolution. So grab a coffee and let's dive into one of the most elegant algorithms in machine learning. Let's start with the basics. Backpropagation, short for backward propagation of errors, is an algorithm used to train neural networks. But what does that actually mean? Think of it like learning to shoot arrows at a target. When you miss, you don't just shoot another arrow randomly. You look at where your arrow landed, figure out what went wrong, and adjust your aim accordingly. Backpropagation does exactly this for neural networks. When a neural network makes a prediction, information flows forward through the network. This is called the forward pass. The network takes input data, processes it through multiple layers, and produces an output. But here's the key. The network's initial predictions are usually wrong. Backpropagation calculates how wrong the prediction is, then works backwards through the network to figure out which weights and biases contributed most to the error. It then adjusts these parameters to reduce the error, making the network slightly better at the task. This process repeats thousands or millions of times until the network becomes highly accurate. Before backpropagation was popularized in the 1980s, training neural networks was extremely difficult and inefficient. The algorithm revolutionized the field of artificial intelligence. Today, backpropagation is the foundation behind virtually every AI system you interact with. Image recognition on your phone, language translation, recommendation systems on Netflix and YouTube, autonomous vehicles, medical diagnosis systems, they all rely on neural networks trained using backpropagation. What makes it so powerful is its efficiency. Instead of randomly adjusting network parameters and hoping for the best, backpropagation provides a systematic, mathematically sound way to improve the network's performance. It enables networks to learn complex patterns from data, making them incredibly versatile. Whether you're working with images, text, audio, or any other type of data, backpropagation can help your network learn meaningful representations. Now, let's build some mathematical intuition. Don't worry, we'll keep this conceptual and focus on understanding rather than getting lost in equations. In the forward pass, each layer takes inputs, multiplies them by weights, adds biases, and applies an activation function. The output of one layer becomes the input to the next layer. At the end, we compare the network's prediction with the actual target using a loss function. This gives us a single number representing how wrong our prediction is. Here's where the magic happens. Imagine you're standing on a hill in thick fog, and you want to reach the bottom. You can't see far, but you can feel which direction is steepest downhill. Gradient descent works similarly. The gradient tells us which direction to adjust each weight to reduce the loss most quickly. It's like a compass pointing toward better performance. Backpropagation uses the chain rule from calculus to efficiently calculate these gradients. Since the loss depends on the output, which depends on the previous layer, which depends on the layer before that, we can chain these dependencies together. Starting from the loss, we work backwards through each layer, calculating how much each weight contributed to the error. This gives us the gradients we need to update the weights. Let's walk through a concrete example. Imagine we have a simple network trying to predict house prices based on size and location. We feed in our input, let's say house size is 2,000 square feet and a location score of 8 out of 10. Step 1. Forward pass. The input layer passes these values to the hidden layer. Each hidden neuron calculates a weighted sum of inputs plus a bias, then applies an activation function. The hidden layer outputs then flow to the output layer, which gives us a prediction, let's say $350,000. Step 2. Calculate loss. If the actual house price was $400,000, our error is $50,000. We square this to get our loss value. Step 3. Backward pass begins. We start at the output and calculate how the loss changes with respect to the output layer's weights and biases. We then propagate these gradients back to the hidden layer, calculating how each hidden layer weight contributed to the final error. Step 4. Update weights. Using these gradients, we adjust each weight by a small amount in the direction that reduces the loss. Step 5. Repeat. We feed the next training example through the network and repeat this process. Gradually, the network learns to make better predictions. Let's discuss some key components. The learning rate controls how big steps we take when updating weights. Too large, and we might overshoot the optimal solution. Too small, and learning becomes painfully slow. Activation functions are crucial. They introduce nonlinearity, allowing networks to learn complex patterns. Common choices include ReLU, sigmoid, and tan, each with different properties. One challenge is the vanishing gradient problem. In deep networks, gradients can become extremely small as they propagate backwards, making it hard to train early layers effectively. Modern techniques like better activation functions, normalization layers, and residual connections help address this. Another important concept is regularization. Backpropagation can sometimes lead to overfooting, where the network memorizes training data but fails on new examples. Techniques like dropout and weight decay help prevent this. In practice, we rarely update weights after each single example. Instead, we use mini batches, small groups of examples, to make more stable gradient estimates. While basic gradient descent works, modern optimizers like Atom, RMSprop, and Adagrad adapt the learning rate automatically and often converge faster. Modern deep learning frameworks like TensorFlow and PyTorch handle backpropagation automatically through computational graphs. You define the forward pass, and they compute gradients for you. The matrix operations in backpropagation are highly parallelizable, making GPUs incredibly effective for training neural networks. What might take days on a CPU can complete in hours on a GPU. Let's see backpropagation in action. In computer vision, convolutional neural networks trained with backpropagation can identify objects, faces, and even generate realistic images. In natural language processing, transformer models like GPT and BERT use backpropagation to learn language patterns from vast amounts of text. Even in reinforcement learning, backpropagation helps train value functions and policy networks that enable AI to master games and control robots. Beyond commercial applications, backpropagation is accelerating scientific discovery, from predicting protein structures to modeling climate change. Let me clear up some common misconceptions. First, backpropagation doesn't guarantee finding the global optimum, it finds local minima, but that's often good enough. Second, more layers don't always mean better performance. Sometimes simpler networks generalize better. Here are some practical tips. Start with simple architectures and gradually increase complexity. Monitor both training and validation loss to detect overfitting early. Visualize your gradients. If they're too large or too small, adjust your learning rate or network architecture. Don't forget data preprocessing. Normalizing inputs can significantly improve backpropagation's effectiveness. Let's recap what we've learned. Backpropagation is the fundamental algorithm that enables neural networks to learn from data. It works by calculating gradients and updating weights to minimize prediction errors. Looking ahead, researchers are developing alternatives and improvements to backpropagation. Techniques like forward-forward algorithms, biologically plausible learning rules, and quantum neural networks may reshape how we train AI systems. If you want to dive deeper, I recommend starting with frameworks like PyTorch or TensorFlow. Practice with simple datasets like MNIST or CFAR10 to see backpropagation in action. The beauty of backpropagation lies in its simplicity and power. With just calculus and linear algebra, we can train networks that perform seemingly magical tasks. What fascinates you most about backpropagation? Let me know in the comments below. If this video helped you understand this crucial algorithm, please like and subscribe for more deep learning content. Thanks for watching, and I'll see you in the next video where we'll explore advanced optimization techniques that build upon backpropagation.